Dear students, welcome again to the class of HS second year. Myself, Dr. Ashim Kalyan, Associate Professor, Department of Physics, SS College, HAilakandi. In the last two videos, we have discussed about atom and atomic models. Today, I will discuss about the photoelectric effect. Before going to photoelectric effect, we will discuss about free electrons and how they emit from metal surface. So, what are free electrons? We all know that the electrons residing in the outermost orbit of an atom are loosely bound and they get detached easily from the atom due to the thermal agitation at room temperature. But although the electrons escape from the atom, they can never escape out of the metal surface. They move randomly in all directions freely like ideal gases. That's why they are also known as electron gases. Since they are free to move within the metal, that's why they are called free electrons. To remove an electron from the metal surface, we have to give an additional energy to the electrons so that they can overcome the surface barrier of the metal. This minimum energy is known as work function of the metal. So we have learned about the free electron, how they form, how they move. Now, what are electron emissions? Electron emissions is the process of emission of electron from the metal surface. It's very simple. Simply the emission of electron from the metal surface. And we have already discussed that to emit an electron, we need an additional minimum energy, and that minimum energy required by the free electron to just leave the surface is known as work function of the metal. Now, what are the different types of electron emissions? That is, electron can be emitted in various ways. First one is thermionic emission. In this process, the energy is given in the form of heat. When a metal surface is heated, then the heat energy is absorbed by the free electrons, as a result of which the free electrons emit from the metal surface. That is, the process of emission of free electrons when a metal is heated is known as thermionic emission. Next one is photoelectric emission. In this case, the energy source is light. When a metal surface is exposed to light of suitable frequency, then the free electrons within the surface can absorb this photon energy and they can emit from the metal surface. Here, the process of emission of free electrons when light of suitable frequency is incident on a metal surface is known as photoelectric emission. Next one is secondary emission. In this case, a strong beam of highly energetic electron are incident on the metal surface, as a result of which the free electrons within the metal surface absorb a part of this energetic incident electrons and they get emitted from the metal surface. So the process of emission of free electrons when highly energetic electron beam is incident on a metal surface is called secondary emission. The last one is the field emission. In this case, the metal from which the electron to be emitted is placed under a strong electric field, and as a result of this field, the electrons emitted from the metal surface. So the process of emission of free electrons when a strong field is applied across the metal surface is known as field or cold emission. So we have discussed about different types of emission process of electron, and our concern is only the photoelectric emission that we have already discussed. Now, what is photoelectric effect? The phenomenon of emission of electrons from metal surface exposed to light energy of suitable frequency is known as photoelectric effect. We have already discussed this, and the emitted free electrons or free electrons from the metal surface are known as photoelectrons, and the electric current constituted by these photoelectrons are known as photoelectric current. Now we will discuss about the experimental setup to study the photoelectric effect. This is shown in the figure. Here a cathode and an anode is enclosed within a glass cube, and both this cathode and anode are subjected to a potential by this battery and potential divider. By this potential divider, we can change the potential across the cathode and anode. This is the window through which we can incident light. This window is made up of quartz, which can only pass ultraviolet light. So ultraviolet light, because ultraviolet light is highly energetic. So when ultraviolet light incident on this cathode through this window, then the free electrons within the cathode absorb this energy, photon energy of this ultraviolet light, and they get sufficient energy to leave the surface of the cathode. If there is no potential across this cathode and anode, then the electron emitted from the cathode surface will be moved randomly in all directions. They will move in this direction, they will move in this direction randomly. But due to the presence of this field, the emitted photoelectrons will move towards anode in straight line. So all these photoelectrons will reach anode to constitute a photocurrent indicated by this micrometer connected in series, and the corresponding voltage across these two is measured by this voltmeter. So by varying potential, we will get a change in photocurrent, and also we will get different photocurrent with a change in intensity of the incident light. So there are different effects of this experiment which are discussed in the next slide, which will be discussed in the next slide. Here, first one is effect of intensity of light on photocurrent. First of all, what is intensity of light? Actually, intensity of light is nothing but the number of photons crossing per unit area per unit time. So if the intensity of the incident light increases, the number of photons crossing per unit area per second will also increase, as a result of which the emitted photoelectrons will also increase, because the free electrons within the cathode surface will introduce more and more photons, and they will subsequently emitted from the metal surface. And as the number of photoelectrons increases, so the photocurrent will also increase. Therefore, the photocurrent is directly proportional to the intensity of incident light shown in the curve. Here, one thing should be mentioned then, that the photoelectric effect is possible only above certain critical frequency, above certain threshold frequency. We cannot get photoelectric effect by all the frequencies by simply increasing the intensity of incident light. So photoelectric effect is possible only when the photoelectric current, only when the frequency is above the threshold frequency. That is, for a fixed frequency above threshold frequency, the photoelectric current increases linearly with the intensity of the incident light. Next, effect of potential on photocurrent. Now, what will be the effect of potential on photocurrent? So, here is the curve. Here the photocurrent. This is the photocurrent and this is the potential. From the curve, it is observed that as the potential increases, the photocurrent also increases and reaches to a maximum, and that maximum is known as saturation current. Here, all the photoelectrons emitted from the cathode surface will be attracted towards the anode. So, there is no more photoelectrons, so current is constant, although we increase the potential. This is the saturation current. For different intensities, the saturation current will be different. Here, three intensities I3, I2 and I1. I3 is greater than I2 and which is greater than I1. So, as intensity increases, the photocurrent also increases. So, for a fixed frequency and intensity, the photoelectric current increases with increase in positive potential applied to the anode. When all the photoelectrons reach the plate, current becomes maximum and known as saturation current. This is the saturation current. When the potential is decreased, the current decreases but does not become zero at zero potential. It is interesting. Here we see this is in this section of the curve. The current potential is zero, but current potential is zero, but current is not zero. So, in order to make the current zero, we have to apply a negative potential. So that current becomes zero. When negative potential is applied to the anode with respect to cathode, photoelectric current becomes zero at a particular value of negative potential, and that particular value of negative potential is known as cutoff potential. This cutoff potential is fixed for a metal and for a particular frequency, threshold frequency, whatever may be the intensity of incident light. If we do not change the frequency of the incident light and changes the intensity of light, then there will be no change in stopping potential. The stopping potential will remain same. Now we will discuss the effect of frequency of the incident light on stopping potential. This is the curve shown. Here we consider the situation where the saturation current is constant, that is for being constant saturation current, and using different frequencies we get two curves. The saturation current is constant, but due to the different frequency the stopping potentials are different. That is, this is already discussed. For a fixed intensity of incident light, the photoelectric current increases and is saturated with increase in positive potential. This is discussed in the previous slide. Now, however, the saturation current is same for different frequencies of the incident light. We may take the same saturation current for different currents, for different frequencies. Current is same, but here is different frequency. So what happens when the potential is decreased and taken below zero? Photoelectric current decreases to zero, but at different stopping potentials for different frequencies. That is, due to the change in frequency, the stopping potential also changes. So stopping potential is directly proportional to frequency of light. Stopping potential is directly proportional to frequency of light. Now, on the basis of the experiment, we will discuss the different laws of photoelectric effect. First one is, for a given substance, there is a minimum frequency of incident light called threshold frequency, below which no photoelectric emission takes place whatsoever the intensity of light. That means the incident light should have a frequency above threshold frequency for photoelectric emission. Second one, the photoelectric current is directly proportional to the intensity of incident light, provided the frequency of incident light is greater than the threshold frequency. That is, if the incident frequency is greater than the threshold frequency, then if we change the intensity of incident light, then photoelectric current also changes, which will be in directly proportional, which is directly proportional to the intensity of incident light. Next one is the maximum kinetic energy of the photoelectron increases with the increase of frequency of the incident light. So the energy of the kinetic energy of the electron depends on the cutoff frequency or threshold frequency, and also on the cutoff potential. So basically, cutoff potential is also related to the threshold frequency. So we can say that maximum kinetic energy is directly proportional to threshold frequency. When the frequency above threshold frequency increases, the kinetic energy also increases. The process of photoelectric emission is instantaneous. This is very important. There is no time lag between the absorption of photons by the cathode and subsequent emission of photoelectrons from the surface of the cathode. It is instantaneous. Now we will discuss whether wave theory or classical theory of light can explain the photoelectric effect. Photoelectric effect cannot be explained on the basis of wave theory of light. Here are the reasons. First one is, according to wave theory, the kinetic energy acquired by the free electrons should increase with the increase in intensity of light. But actually the maximum kinetic energy is same for different intensities. This is very interesting. Classically, or according to wave theory, the energy is directly proportional to intensity. So as intensity increases, kinetic energy also increases. So by increasing the intensity only, we can get any kinetic energy, or rather we can induce photoelectric effect in accordance with the classical theory. But experimentally it is found that above the threshold frequency only we can produce photoelectric effect. Below threshold frequency we cannot induce photoelectric effect whatever with the intensity. Moreover, it is also observed the maximum kinetic energy is same for different intensities. It is shown in the effect of potential curve. Second one, according to wave theory, the photoelectric effect is possible if the metal surface is exposed by an intense beam of light irrespective of any frequency. Already we have mentioned that according to classical theory, photoelectric effect is possible by only increasing the intensity irrespective of the frequency, but practically it is not possible. It is only possible if we take the frequency of the incident light above the threshold frequency. The last one is, according to wave theory, there should be a time gap between incident and emitted photoelectron, but actually the process is instantaneous. So according to classical theory, there should be a time of absorption of photon by the free electrons within the cathode, and so there should be a time lag between the emission and absorption of photon. So classical theory fails to describe the photoelectric effect. So we need a new theory to explain the photoelectric effect, and that new theory is nothing but the quantum theory of light. The quantum theory was first introduced by Planck in 1901. We all know about Planck's law, E is equal to h nu, where h is Planck's constant and nu is the frequency of the emitted light. Einstein used this Planck's theory, that is quantum theory, and introduced the law of photoelectric effect. When a photon of energy h nu falls on a metal surface, the energy of the photon is absorbed by the electron and is used in two ways. This is the photoelectric. This is the photon emitted on the metal surface, and a part of this energy is overcome due to the work function. To overcome this work function h nu naught, and the remaining part will use to give kinetic energy to the photoelectron. That is, a part of energy is used to overcome the surface barrier and come out of the metal surface. This part of energy is called work function, y is equal to h nu naught, and the remaining part of the energy is used in giving a velocity v to the emitted photoelectron. This is equal to the maximum kinetic energy of the photoelectrons, where m is the mass of the photoelectron. So, according to law of conservation of energy, h nu is equal to phi plus half m max square, because this is the incident energy and this part is the energy used to overcome the surface barrier, and this is the energy used to give kinetic energy. We also know work function phi is equal to h nu naught, so putting the value we get h nu naught plus half m max square. Rearranging this equation, we get half m max square is equal to 8 into nu minus nu naught. This is the famous Einstein's photoelectric emission. Now we'll see whether Einstein's equation can verify all the experimental laws of photoelectric effect. We all know, according to Einstein's photoelectric effect, half m max square is equal to h into nu minus nu naught. If nu less than nu naught, then half m max, that is kinetic energy, will be negative. Energy can never be negative, which is impossible. That means kinetic energy, especially kinetic energy, cannot be negative, because here the electrons are emitting from the metal surface. So with negative kinetic energy, electrons cannot emit from the metal surface. Therefore, for photoelectric emission, nu should be greater than nu naught, that is, this should be positive. So this is the first condition of threshold frequencies. This indicates the first condition, that is, the incident frequency must be greater than the threshold frequency. Second one is, since one photon emits one electron, so the number of photoelectrons emitted per second is directly proportional to the intensity of incident light. It is already discussed. As we increase the intensity, the number of photons also increases, and due to the increase in number of photons, the subsequent number of photoelectrons will also increase, and it constitutes a large photocurrent. That is, photocurrent is directly proportional to the intensity of incident light. Next part, here the kinetic energy is equal to h nu minus nu naught. Here nu naught is threshold frequency, which is constant for a metal, and h is Planck's constant. So half m max square is proportional to nu. So it's clear that half m max square is proportional to nu, as h and nu naught are constants. This shows that kinetic energy of the photoelectrons is directly proportional to the frequency of the incident light. Above threshold frequency, as the frequency increases, the kinetic energy of the emitted photoelectron also increases. Next one is, photoelectric emission is due to the collision between photon and an electron. That is, photoelectric emission takes place when the cathode plate absorbs the incident photon and subsequently electron emits. So there should not be any time lag between the incidence of photon and emission of photoelectron. That is, the process is instantaneous. Actually, about, there is a time lag of about 10 to the power minus 9 millisecond nanosecond order, which is negligible. Now we have observed that the quantum theory of light can easily explain all the experimental laws of photoelectric effect. So, whereas the classical theory fails to explain the photoelectric effect. Now we will discuss a few applications of the photoelectric effect. Photoelectric effect can be used in different ways and different fields. First one is automatic fire alarm. This fire alarm can detect the fire in some place. When the alarm is exposed to fire, it ranks up. Second one is automatic burglar alarm. In this case, a laser beam is introduced in the entrance. When a thief tries to enter through the gate, then due to the obstacle of his body, the laser beam, the circuit breaks, the circuit which constituted by the laser beam breaks down, and the alarm ranks up. Next, we can easily reproduce sound in cinema and films by using photoelectric effect. Next one is to locate the flaws and holes in the finished goods. That is, with the help of photoelectric effect, we can find any cracks or holes in industrial finished goods. And it is also used in astronomy, so basically to detect the temperature of stars. And last one is automatic switching arrangement of street lights. It's very important, and you can easily use these two street lights, because in daytime the light is incident on the switch and it will be in on off state, but when in the evening there will be no, whereas in the evening there will be no daylight, as a result of which the switch will be on, giving light to the streets. So easily we can use photoelectric effect for the switching arrangement of street lights. There are many more applications of photoelectric effect. We are not going to discuss this for today. We are concluding here. Thank you.